Hello YouTube, this is Aditya here, back with another video, and today we're going to look at how big companies like Microsoft, Google, Facebook and all these companies reduce the latency of their application using a concept called as Anycast. Okay, so before we get started, I have two quick things to talk about. This is my first whiteboard video, so I'm not really sure how good the video is going to be or how good the recording of the board is going to be. So I'm going to keep improving upon it by receiving your feedback. So that is really important. Please do give me feedback based on the clarity or anything, the voice. This is a new microphone that I have as well. So that is the first thing. Second thing is I'm looking at reaching 100 subscribers after this video. So the next thing that I'm planning for you guys is a complete playlist on how operating systems work. So that is going to be quite interesting as well. And I'm going to plan, or I'm going to start working on that only after I reach 100 subscribers. So I'm currently at 90 and I just need 10 more subscribers to reach 100. Okay, that being said, let's quickly get started with the topic for today. So let us start off by taking a very simple example. Let's say I have developed a social networking website and I've registered the domain name abc.com. And let's say I have my servers for this website in America. Okay, just to clarify, I have drawn like different regions around the world. This stands for United States, and here we have Africa, here we have India, and here we have Australia. Okay, this is just for reference. So let's assume I have developed a social networking website and I'm hosting it in a data center in America. Okay, so what will happen is this is going to be a global website, right? Everyone in the world should be able to access this. I want a lot of traffic coming across the globe. I want to connect all the people across the globe via my website. Okay, so here what we will be doing is we are going to host this website on the servers which are present in this data center. Okay, the next step would be to see what all problems can occur in this case, right? So let's say there is a user in India who's trying to register on the social networking site and who's trying to become a member. What's going to happen for the Indian customer or the Indian user is the Indian user will have to travel all the way till this data center to talk to this application because it is present only in one data center, right? So then this is where the latency comes into picture. However fast the internet is, it is going to take more time for an Indian user to access this website as compared to a person sitting in US. Okay, so this is kind of a partiality that you're having, which isn't good. You would want to reduce latency as much as possible to all the users across the world, right? So what you start seeing is the users who are trying to connect to the website start seeing a lot of latency or a lot of slowness in the page loading. Okay, and sometimes they might also get really angry and they might not even register to your website because it's taking a long time to load. The simplest solution here, which I can think of right now, is to have like one data center in every region, right? You just have your application hosted in every region. Okay, so since you're considering only 4 regions here, okay, you have your application installed in every region. By this, the problem that you will have is to synchronize your application. So let's say you want to deploy a latest version of the website. It would be difficult for you to deploy across all, but that can somehow be managed. That is not at all a problem as of now. The next thing that you would want to understand here is how would the Indian customers be routed to only the servers which are in India and do not have to go to US to access the website. So this is done by using DNS again. And if you haven't watched the DNS video of mine, I would recommend you to watch that. So let's see what happens. Okay, so let's assume there is this is our website and we buy 4 IPs. Okay, because there are 4 different regions, we're going to buy 4 IPs, and let's assume the IPs are 1.1.1.1, 2.2.2.2, 3.3.3.3, and 4.4.4.4. Okay, for simplicity, we're just going to call them 1.1, 2.2, 3.3, and 4.4. Okay. What we're going to do is we're going to associate each of these IPs to each of these regions, right? So we're going to have 1.1 here, we're going to have 2.2 here, we're going to have 3.3 for India, and we're going to have 4.4 for Australia. Okay, so now we have kind of isolated the website to different regions. Okay, the next step would be to have a smart DNS reply based on the region. So let's assume there is an Indian user who's trying to access the website which is in the data center which is present in India. What we would require is, let's assume this is the entire DNS process which happens. So the Indian user contacts the DNS, requests for an IP of abc.com, and the DNS should be smart enough to recognize the IP and the geography. Okay, so we're going to have a mapping based on the user's IP, okay, from where the user is coming, and we are going to accordingly send him to the IP which is 3.3 here. Okay, so in our DNS table, we are going to, or the DNS software or whatever we are using, we are going to look at the geography of the person who's coming. Okay, let's say a person is requesting from India. We're going to ideally send send the response as 3.3 because we want the Indian user to contact the server present in India. Okay. Now here, as you see, there is a wastage of a lot of IPs. This is considering just 4 regions. There are multiple regions in the world that you will have to cater to. So you will require one IP for each region if you go with this method. Okay. And what else can happen here? So your DNS has to be smart enough to basically compute the IP addresses of the entire world every day or whatever duration you set it as, and it should be able to associate that with the geography. So why am I telling this? Let's think about that a little bit. So let's assume you have an internet connection to your house and you have been assigned an IP address. Let's assume it's a public IP address for now. You have been assigned a public IP address, but there is no guarantee that that IP address belongs to you forever. The ISP can, refresh your IP address. He can allocate that IP address to someone else, unless you have a deal with the ISP saying this is a static IP address that I want. Okay, so because of this, a lot of IP addresses across the world between ISPs keep getting reshuffled. Okay, the IP address that I have today might all of a sudden belong to someone sitting in the US just in 2 days. Okay, so what will happen is the person who's contacting from US, the DNS here, the software that you have for DNS, looks at the geo and IP mapping. It gets this IP address from the person in US. It maps it to India because this IP belonged to an Indian user before, and it's going to send the user to the Indian DC. Okay, it's going to send the user to this server that we have in India, and again it's going to increase the latency for the person who's accessing from US. Okay, we want to avoid this as well. This is not a good thing to happen. Okay, the next thing that we can see is, let's say the data center in India went down due to some reason. Okay, let's assume there is a power outage, or let's assume it has been hit by a storm or some natural calamity. So if this data center goes down, and let's say an Indian user is trying to access the website, it's very common that the data center has gone down, but the users are still alive. They still want to access the website, right? They are not going to go anywhere if the data center is down. So what will happen is the Indian user will go to the DNS. The Indian user will ask for a IP for the website abc.com, and since the DNS returns 3.3, it tries going to the server which is down. Like the server doesn't exist; it is being blown out. Okay, and what happens is all of a sudden Indian users are all blocked from accessing the website just because one data center went down. All these Indian users are not able to access the website. This is a pretty bad scenario. So how do you solve that? What we do is we have something like a health check, okay, built into the DNS. Again, we are overcomplicating DNS. It's supposed to be as simple as possible, wherein you request for a IP for a website and it just responds. But here we're kind of complicating it by associating geo IP to it. And now we are also building one more smart solution, which is a normal health check that it does to the service. Okay, so this is an additional service. Let me put it in red. So you're adding an additional health check, okay, which keeps contacting the Indian DC, the servers in Indian data center, to see if it is still sending a response. So as soon as this data center goes down, it will update in its DNS that this IP does not exist anymore, the servers are down, and it will start rerouting it to the second nearmost. Let's say it's Australia, it's going to start redirecting all Indian users to Australian data center servers. Okay, so this is what will start happening once the data center goes down. But the catch here is there is something called as time to live in DNS, right? As we discussed in our previous video. So what will happen is you have a TTL which is set for this DNS, and this can be instantly changed to serve this. But then there are multiple levels of TTLs which have to be bypassed. So for example, all the Indian users will have a TTL in their cache, in their local operating system cache, right? So that has to expire. Then let's say the browser has a TTL cache, that has to expire. And only after all of that is when it will hit the DNS server again, and that's when it will get a response for 4.4. And only after that, the Indian users will start accessing Australian servers. So basically what I'm trying to explain is there is a small amount of duration when the entire service or the entire social networking website is down for some users. Okay, and in our case, it's going to be Indian users. We wouldn't want this to happen. So here's where the next solution comes into picture, which is Anycast. Okay, and let me quickly erase this and let's look at how Anycast works. We did realize that geo IP based DNS solution was not working really well for us. So the next thing that we can look at is how to utilize Anycast IP concept to do the same thing here. Okay, so if we look at it, what we will require is we have our social networking website again, abc.com, and we have one IP. Okay, we have 1.1.1.1.1, and we are again going to just call it 1.1 for simplicity. What we're going to do is in the DNS servers across the globe, we are going to update the IP of abc.com as 1.1. Okay, so in this case, when we are utilizing or when we're making use of Anycast, we are going to buy only one IP for the entire website. We do not require multiple IPs. Okay, so once we have 1.1 associated with abc.com, what you do is you do not really require the entire data center to be present in all the regions. What you will require, however, is something called as a POP. Okay, this stands for point of presence. So basically, we have a point of presence for this website or for this service across the world. Okay, so we have a POP in Africa, we have a POP again in India, we have a POP in Australia. Okay, just to clarify things, you do not necessarily need to have only one POP in one region. You can have like thousands of POPs. It just depends on how much money you're ready to shed and how much of overcomplications you require in your entire architecture. Okay, so now coming back, let's see what happens when someone tries to access abc.com. Okay, some Indian user again, let's take the same example. The Indian user tries to access abc.com. He queries the DNS service which is present here. Okay, and what happens is the DNS responds with 1.1.1.1, okay, or 1.1 IP. And the Indian user is supposed to hit this IP to be able to access the website. Now, what's going to happen is the Indian user is going to access this data center again because this is the only place we have associated this IP. Okay, by associating an IP, what I mean is we are going to bind the IP to the server and we are going to announce it using BGP. Okay, the BGP router which is present at each POP should start announcing that the server inside the BGP router or behind the BGP router owns that IP. Okay, so basically BGP peering is covered in one more video of mine, and I will just link it to the video on top here, so you can go check that out as well. So based on BGP peering, what is going to happen is each of these POPs will have a BGP router in front of them, and they will start advertising that they own 1.1. So the data center here will start telling I own 1.1. The POP here will start telling I own 1.1. The POP here in Australia will tell the same, and the same in India as well. So once the announcements start taking place via BGP peering and BGP announcements, what will happen is the routers near the POP. Okay, let's assume these are the routers. Okay, all these routers start computing routes to the nearest IP. Okay, let's assume this user in India wants to access 1.1. All these routers basically have routes to 1.1. Okay, let's just take one router here as an example. Let's assume This router is where this user is going to hit. This router has routes for all the 1.1s which are present. Okay, it knows that it can reach 1.1 in maybe 50 ways or whatever, and it starts computing the path which is the best for it. Okay, in this case we can talk about maybe the shortest path, the least number of hops to reach 1.1, or maybe the least amount of time that it takes to reach 1.1, or the maximum bandwidth having a route which it can reach using the route. So all those are pre-computed, and let's assume we have 50 routes present, and it is going to select the POP which is announcing 1.1 in India, because that is going to be the shortest or the least latency path that it can reach, right? So basically this router will find out a way to reach 1.1 in the least time or the shortest way possible. And what happens is the routes, each of the cable which is connected between two routers has a weight associated with it, and that's how the entire weight for the path between this router and the POP is computed. Okay, similarly it does for all the POPs in the world, and it is able to tell that the Indian POP is what it can reach the fastest. Okay, that's how it hits the Indian POP, and that's how the Indian user is routed only to Indian POP. This is a small trick that we have in BGP, which we use, and we are able to serve traffic based on the geographic locations or the closest server to the particular user who's requesting. Okay, this being said, what is going to happen now is all the users in India are going to get redirected to a POP which is the closest to them. Let's assume there are two POPs in India as well. The users who are closer to the POP or the least time they will take to reach to the POP will be redirected to the particular POP. So let us look at the same problem that we had encountered in the previous situation, right? Let me erase these routers. We do not really require so many routers for now. It's just making this look bad. So let us assume this POP goes down. Okay, what is going to happen in that case is all the Indian users who are trying to access the server in that particular POP will no longer be able to access it, just like our previous scenario, right? So what will happen now is the user will again contact the DNS will respond with 1.1, and the user is going to talk to the next router, and basically the paths which are computed here are going to change. Okay, there is a check which keeps happening as soon as this POP stops announcing 1.1 because it goes down due to several reasons, is when all the routers will rechange their paths. They're going to reconfigure the entire path, and they're going to see which is the next nearest or the next closest POP that they need to hit in order to access the same website. Okay, so the users are no longer going to go to this POP, but they will go to the POP in Australia, assuming that is the closest one to them. Okay, and since the users are redirected to Australia immediately, this is not going to show any downtime for the particular social networking website, whatever happens. Even if this POP goes down, they will start getting redirected to the next closest POP. The latency for the users might increase, but it's going to increase by a very small amount, considering our previous scenario where the entire site would have gone down for several minutes or whatever till the TTL expires, right? So this is going to be a much better solution when you want your site's latency to be reduced and it to be available for a longer duration of time. The next thing that you can also look at is, let's consider a DDoS attack happening on our site. Okay, let's assume there is a hacker sitting somewhere. Okay, and what happens in a DDoS attack? Let me quickly explain that. So he's going to collect bots across the internet. He's going to compromise a lot of users' computers. Okay, let's assume there are 5 users in Africa, just for example, and there are 5 users in America and 2 users in Australia whom he has hacked into, and he's going to use these servers or these computers to launch an attack. He's going to basically use these, how many computers? 5 plus 5, 10 plus 2. The hacker owns 12 computers now of innocent users, and he's going to use these 12 computers to start accessing the social networking website as many times as possible. So he's going to basically try putting a lot of load on this particular website. Okay, and once the load increases, the server's resources starts getting exhausted, and that's how the legitimate users or whoever want to actually access the site are not allowed to access because of resource constraints and the servers going down and all that. So in our case, since we're using Anycast here, let's look at what will happen. Or let's look at a scenario, what would have happened when the Anycast wasn't used before. Okay, so when the Anycast wasn't used, we had only one data center in US and we had 12 computers attacking the data center in US, right? All the traffic across the world would have hit the same data center, and this would have led to 12 computers accessing the data center at once, okay? Obviously, it's not going to be just 12 computers. There's no website which will go down in 12 computers. So this is just for explanation, but just multiply that by like several lakhs or something. Okay, just like 12 million users trying to access US data center at once. Okay, this we hadn't considered for this load, so it is natural for the servers in this data center to go down, which means the application is not accessible to the entire world. No one in the world is able to access this website just because one DC went down. Okay, now let's look at a scenario where we have implemented Anycast and now the hacker launches the same attack again. Okay, so what is going to happen is these 5 users are going to go to the DC in US. These 5 users are going to go to this POP in Africa, and these 2 users are going to go to the POP in Australia. So basically what we're doing is we're distributing the load. Okay, we are not allowing the hacker to bring down the website just because he's compromised 12 systems across the world. Okay, this will basically allow the users to legitimate users to still continue accessing the website. So this has been a really good solution to mitigate DDoS. But again, hackers are evil and they're able to come up with new solutions. So what they do is they start compromising a lot of hosts in the same region. Okay, in US itself, they get 12 systems, they compromise 12 systems, and they start attacking the same data center, in which case the entire DC will go down. Okay, and it will be unavailable only for the users in America. Okay, the website will still be accessible for the rest of the world because all the other POPs are still active. Okay, so this would still mitigate it to a certain extent, but not completely mitigate the issue. Okay, so I had one last thing to cover. So all of this is assuming we are going to have only IPv4 and we are going to have this BGP hacky way to spread the traffic to each POP. Like we send the traffic to the POP based on the IP and based on the closeness of the POP to the particular user. In case of IPv6, they have Anycast implemented inside IPv6 itself. So all the routers which understand IPv6 have certain number of IPs allocated in every subnet for Anycast. Okay, so that simplifies the entire process. You do not need the hacky way of BGP announcements of the same IP across the world. Okay, so you do not require to do all of this because when you shift to IPv6. Okay, that is all I had for this. I just had one interesting question for you guys before we drop off. Let's assume there are 2 POPs. Okay, this is POP 1 and this is POP 2. Okay, and there is a user who's trying to access the same website again from one of these 2 POPs. Okay, and this is going to be the route for POP 1 and this is going to be the route for POP 2. Okay, let's assume this is the user here. So now what happens here is, let's assume the weight for both of these paths is 50. Okay, it's computed to be 50. Now which POP do you think the user will be routed to? Because both the POPs have got the same weight, so it is up to the user to it's not up to the user, it is up to the entire network to decide which POP to route the user to. Okay, this is an interesting challenge that you can come up with a solution, and then you can let me know in the comments as to how you would go about solving this when the user is equidistant or equi-weighted across 2 POPs. Which POP will the user choose? Okay. One more interesting thing that you can read across is something called as route leaking. Okay, route leaking happens and the users are basically flapping between 2 POPs. Okay, and this basically instabilizes the connection for a particular user. He's going to POP 1 once and he's going to POP 2 the second time, which is really unstable for the user. Okay, and this does not work in case of TCP because you need to set up the 3-way handshake first and then you start accessing the data. And when you have SSL over this, it overcomplicates it even more. So the best thing about Anycast, it is very much suited for applications which are stateless, okay, which do not require continuous interaction with the user and storing the user's previous session information and all of that. That's when Anycast works brilliantly. And the most widely used application for Anycast is our DNS root name systems. Okay, all the root servers in the world, there are like 13 root name servers. They have used Anycast to be able to distribute load and to be able to reduce the latency for the users accessing the DNS servers and getting a response back. Okay, so this has helped a lot in getting the IP of a website as quickly as possible. I hope you guys understood what Anycast is used for and how it works in the real world, and how big companies are able to leverage the concept of Anycast to reduce the latency of the applications that their users are using. I hope you guys are able to implement this in your own organizations if you're able to. That is all I had for today's video. I hope you liked the video and you took away something from it. Please do share the video and subscribe to my channel, because there are just 10 more subscribers that I need to cross 100 subscribers. I would really appreciate it if you just put in your comments in the comment section as well to give me more feedback about how the video went. Thank you for watching, and see you all in the next video.